The style of exam often dictates how you study for the particular test. You know, when I was a student at UCLA, I transferred, I had to just redo how I studied. The reason is the typical exam at UCLA was like 4 questions. 4 questions, and so what do you study for 4 questions? Well, you have to study everything, because if you miss something, that's like 25% of your grade is gone. So if you couldn't answer one question, you took a big hit in points. And so that's one of the reasons why I told you, like, I like to memorize everything in the lecture so I didn't miss anything. And I never liked that, because if I had missed one thing and it was on the exam, then you're basically screwed. You know, you lost a lot of points. So the exams I like to write aren't like that. I like to have a lot of questions. A lot of questions not worth that many points. So if you didn't happen to know that, or you didn't happen to study that particular topic, it's not going to be fatal for your exam score. And so take a look at this on Canvas. Let me see. Open. So this is last week. And I have a lot of multiple choice questions here. Here, unfortunately, there's no partial credits. It's 2 points. So it's not that many points if you miss one. So you either know this or you don't. But let's see, I had a 36 multiple choice. So what I'd like you to do before the test is to pick up the Scantron for me. It's going to be a Scantron 882E, I think. This is the form you want. No, there are 50 questions per side, and you can get these off Amazon, or the bookstore has packs. I don't think they have a 25 pack. I think they have a 6-pack. In the library, you can buy individual ones. And you'll need this for all the exams, so you'll want to probably get a pack of them, the 882E. And then there's some free response questions here. I got a little bit behind schedule here. So in this, I was on schedule this particular semester. So this question is kind of at the end of chapter 4. That type of material. There's some more challenging stoichiometry problems. So we'll touch on chapter 4, but I'm not that far, and I haven't finished chapter 3 yet. So what we'll do for the test next week is I'll probably limit the amount of chapter 4 on there.
What is Maxwell-Boltzmann?
What is Maxwell-Boltzmann? Did I ask that on here?
Yes.
Question 34.
Question 34.
Oxygen molecules at room temperature share a Maxwell-Boltzmann shaped distribution of energies. And I said, oh no, I missed something.
No, you didn't miss anything. Each semester I kind of get off on tangents. And so this particular semester I started talking about energy quite a lot. And so I was off on an energy tangent. But if I'm going to spend 15, 20 minutes talking about energy in class, I'm going to just throw it on the test. And so that's what I did. You didn't miss anything. Maxwell-Boltzmann's talked about in chapter 6.
Oh.
So don't worry about it for this one. I don't know why I started talking about Maxwell-Boltzmann. But this is true. The answer to that.
Gee, thanks.
Maxwell-Boltzmann distribution has a different name. Maxwell-Boltzmann is called a thermal distribution or thermal population distribution. It's just your normal thermal distribution. So forget about the same thing. There could be little, like I said, a lot of tests are just recall, and so I don't really recall what I did in everything in this particular semester, but all these multiple choice questions are like recall questions. So I probably talked about Maxwell-Boltzmann for some reason, but it was introduced a bit too early, probably. I also talked a lot more about oxidation states. So there's another question that you're not going to get on this one. I went into oxidation states a lot more in this. I don't know why I was going so much faster. I seem to have a lot more time, or maybe I'm getting older and slower. But number 24. What are the oxidation states of the two carbons in acetic acid? They aren't the same. They're different. Do you know how to determine the oxidation states of the individual atoms in a molecule? Let's say you have a gigantic protein. The rules for oxidation states that are listed in chapter 3. Chapter 3. Those rules give you the average oxidation state of that element in that molecule, but not all the carbons are the same in acetic acid. These two carbons are quite a bit different in terms of what we call the redox properties. And so when I look at these two carbons, and so maybe you already know how to do this, maybe you don't, but there's no set of instructions in chapter 3 for that. And so that's another question that, the situation is if you know what I talked about in lecture, then you'd know, oh, I didn't miss that. Instructor never talked about that. Yeah. So that's a good catch. So the MESA coordinator, unfortunately the MESA coordinator conflicts with this class, but they had never covered this in Chem 1A. I was talking to her about it. That could go for other questions. I haven't looked at this since 2 years ago. But a lot of these are okay. The other thing is we were using an earlier edition of the book 2 years ago as well.
Don't worry, so are a lot of us.
All right. And then I got a lot further along in organic than I did. And so I had them memorize a lot more stuff, like a lot more substituents. I think the organic section was a little bit more in depth than the previous editions. So we were doing way more substituents. But these, you don't really, this won't be difficult. The longest chain of carbon atoms is how many? What's the number? 3. 1, 2, 3. And then this is an oxygen, so that's not a carbon. And this is a common trick question in organic chemistry. These Lewis structures are written with no regard to the actual structure of this. I mean, everything's flattened out. So this is not zooming in, is it? It's not 3. What is the longest chain of carbon atoms?
It's crazy.
It's 4, yeah. It's 4 because we have to take a right turn here. So we go 1, 2, then down, 3, 4. Longest chain is 4. So the parent chain is called bute, or bute. Is it? Do you guys recall? I did mention, I think on the first day or the second day or something, about problem-solving methods. You know, the most common way we solve problems in chemistry is via dimensional analysis or the conversion factor method. But what are some other techniques that you're going to be hit with sometimes in solving problems? Guess and check, yeah. Guess and check is another. Any others?
Hope and pray.
I'm sorry?
Hope and pray.
Yeah, that goes for all problems. I guess that would work. Some problems you solve algebraically, like temperature. You know, degrees Fahrenheit is equal to 9/5 degrees C plus 32. And then there are some problems that you solve using two equations, two unknowns. Right? Do you remember that system of equations I talked about briefly? System of equations, we could have solved the ethanol problem, blood alcohol content, using a system of equations there, but I didn't want to set up a system of equations. In fact, I like to avoid setting up a system of equations, do it separately. So we'll look at that some more, probably on Monday. But dimensional analysis, you're going to solve like more than 90% of the problems using dimensional analysis or conversion factor method. And so I had a question this morning about a problem in the homework. Not this one. Sorry. And I might as well talk about this. Yeah, sometimes we get hit with different percentages and it confuses things, so we have to keep track of all the percentages that we deal with here. If it can be done with 100% efficiency, what mass of hydrogen gas would have to be processed to obtain a sample containing 2.70 times 10 to 21 hydrogen 2 or deuterium atoms? And so normally the first thing I do is 100% efficiency. What does that mean here in this particular problem? What should I do with that 100%?
You don't lose anything and it all reacts.
Yeah, you don't lose anything. And so if you transfer your white precipitate from the beaker to the Celis crucible filter with 100% efficiency, what that means is you got everything in there. You didn't leave anything behind. And so that's what they're talking about here. And so in this particular case, I'm not going to worry about this 100% efficiency. All I'm going to think about is if we can remove the deuterium from a hydrogen sample with 100% efficiency, then and that might be hard to do because what you need to do is you need to extract all the deuterium out and leave all the hydrogen 1 behind. And so have you tried this? How many people got this? Was this pretty straightforward, this problem? Or was it okay? So where should I start? Well, I'm given one more thing, two more things actually. This is a problem from Mastering Chem. And so what were the other two things I was given?
Probably the prevalence of deuterium in a hydrogen sample.
Okay.
And then probably the varying masses of each.
Yeah,
So you need.
that's what I was given. I closed it. So let me take a look at the problem again here. So, since I'm behind, I extended the due date today for Chapter 4. We're going to have the complete assignment due with Exam 2. What I think I'll do is I'll just put in some simple stoichiometry problems for this exam.
You extended the due date for the homework that was due on the 15th, or the other?
Just Chapter 4.
Oh, okay.
Chapters 1, 2, and 3 are still due as scheduled. Chapter 4 has been pushed out because I don't want to collect just part of the assignment. I want to collect the whole thing. So this problem is a Chapter 2 problem, so let's go back to Chapter 2 here. And I think that was number 18.
Did you send me the weights for my lab?
No, it wasn't. What number was that? 17. Check that. Actually, it looks like most people got this. 85.7%. Was this pretty straightforward? Did you get it, Kiana? You use the AI, ChatGPT? Oh, an AI that talks you through the steps. Okay, what if you didn't have the AI? Well, let's take that into consideration. And so we have some other information here. We have the atomic mass of deuterium, and we have the percent abundance, isotopic abundance, 0.015%. And so I'm going to incorporate those in here. So deuterium has an atomic mass here. I'll just move that. I guess I already did that. And the percent abundance of deuterium is 0.015%. That's for deuterium. So hydrogen is a diatomic element, and so it forms H2 molecules. So hydrogen gas would be H2. And so how many different H2 molecules exist in nature, in a natural sample? 3? Okay, what are they?
They're just like 2 normal ones, 2 heavy ones, and then a mix of a heavy and normal.
Okay, 2 heavy ones, and then a mix. And so if I pick the left one as an H1 and the right one as an H2, that would be one of the mix. And the other mix would be what? H2 on the left and an H1. Can you tell the difference in mass between these two? No. But we consider both of them. Why do we consider both of them? We would have to consider both of them, even though they weigh exactly the same. Because there are 2 ways of making this. If there are 2 ways of making this, what happens to the percent abundance is it doubles the percent abundance. And so that's the only reason we consider both of them. And then 2 of the light ones. So let's do 2 of the light ones, H1 and H1. Out of these, which one will be the most abundant? 2 of the light ones, but we don't want 2 of the light ones. We want ones that are only H2. So 100% efficiency means we're going to separate H2 with 100% efficiency from all these others. And so what we're going to be left with is just pure H2H2. That is pure, what I'm going to call deuterated hydrogen. Deuterated hydrogen. And so that's what they're talking about. So we already have 100% efficiency. We know that we're going to have 100% deuterated hydrogen. So what should we do for solving this? What we should do for solving this is I want 2.70 times 10 to the 21 deuterium atoms. Now, mastering chem has a scrambling function. So what happens is it'll change the given. And so you might not get the same answer as your friend or neighbor because this might change here. So I'm not sure where we should go. Where should I go next? If they want the mass of hydrogen in a sample containing, all right, so I have a sample that contains, to obtain a sample that contains this, many deuterium atoms, I know how much each of those deuterium atoms weigh. It's 2.0140 U. So one deuterium atom weighs 2.0140 U worth of deuterium for every deuterium atom. Is that what they want? Oh no, they want molecules, so maybe I shouldn't go this way. If they want molecules, then how many deuteriums in a molecule? So let's skip that one there. And then I'm going to go 1 molecule of the heavy hydrogen, the deuterated hydrogen, requires how many atoms of deuterium? And so this is just from the formula. So if I have an H2H2 molecule, that consists of 2 H2 atoms. And so this is the composition of the formula. And so now I have the molecules of deuterated hydrogen. And then I know how much a molecule of deuterated hydrogen weighs. I just have to double the mass of deuterium. In other words, a molecule of deuterated hydrogen weighs 4.0280 U per deuterium or deuterated hydrogen molecule. And they want the mass in grams. So if I have this many deuterium atoms, how many grams of deuterium do I have? And so what I need to do is I need to get rid of the U and convert that to grams. Do you remember the relationship between the U and the gram?
Some tiny number, right?
I'm sorry?
Some tiny number, right? I had to look it up when I was doing mastering chem.
Yeah, but you know, you should be able to figure it out. You should be able to derive the relationship between the deuterium, not the deuterium, between the atomic mass unit and the gram. Do you remember we did that in class? The relationship between the U and the gram.
It's 1 it's like 6.022 times 10 to the 23 Ju per gram.
Yeah,
Do
that's
we
it.
do that from carbon 12?
Yeah, we did that from the definition of the
Of the mole.
mole and the definition of the AMU,
So
and
you use the grams per mole
of carbon 12, right, and the AMU mass of carbon 12.
Which is 12, right?
What?
Which is 12.
Which is 12. So this, like this, we did it in class, right? And so this would just be a recall question, but imagine that question was 25 points on the midterm and you forgot the relationship between the U and the gram. And so that's the reason I studied the way I studied. I studied to try to memorize everything that was covered in class so I wouldn't get hit by a 25-point loss, which I did get hit with 25-point losses before. And it's not fun. So, so just be aware of that. And I hated that. I hated that, and so that's why my exams are like they are. Anyway, or you could just remember it. I mean, at least this would be worth partial credit. If you didn't derive this, you'd still get some credit. And this is an easy number to remember, isn't it?
It's Avogadro's number.
It's Avogadro's number, right. And so we get the grams of deuterated hydrogen molecules, correct? And so that would be 2.7 times 10 to the 21 divided by 2 times 4.028 divided by 6.022 times 10 to the 23rd. And that comes out to 9.029 times 10 to the minus 3 grams of deuterated hydrogen molecules. Or this would be 9.03 milligrams worth of deuterated hydrogen molecules. Is that what they're asking? Actually, it's not what they're asking. What are they asking?
Weight in grams.
They want the weight in grams of, not the deuterated hydrogen. They want the weight in grams of hydrogen. So basically, I'm going to end up with 9.03 milligrams of this stuff. But in order to get 9.03 milligrams of this stuff, how many grams of this stuff do I have to have? Well, isn't it 100%? Isn't it with 100% efficiency here that I collect this? So isn't it just 9.03 milligrams? No, it's not, because there's another percentage, and that other percentage is percent abundance. And so we have to look at a different percentage, and we have to keep track of all these percentages. So percentages, parts per million, parts per billion, all those things are very important to keep track of. And so I want to know, what is the percent natural abundance of the deuterated hydrogen? Do you guys remember how to do percent natural abundance of deuterated hydrogen or of any molecule? And so I know deuterium is 0.015% abundance. So do I do 0.015% times 0.015%, and then I'll get percent squared? Is that correct? No, so tell me the formula for the natural abundance of this. Mm-hmm.
Wait, is that like, well, because what I would do is I would just make them decimals, and then I would
That's what I do.
multiply them, and then multiply by 100 to get the percent.
You could do decimals, but when I read decimals, it's hard to make physical sense out of the decimals. So for example, if I represent this in decimal form, it would be 0.00015. And then you think about the units. What are the units of this? What the units of this would be what? Would it be, okay, if it's part per hundred, Okay, we're used to doing that. So it's going to be 0.015 out of 100. And so it's 0.015 what out of 100 what? So automatically people think, oh, it's 0.015 grams of deuterium per 100 grams of hydrogen atoms. So if I had 100 grams of hydrogen atoms, then 0.015 grams of that would be deuterium. Is that true or false? False. False? True? That's false, right? It's false because this is not a percent by mass. They don't tell us that. This is a percent by atom, molecule, or mole. In other words, it's percent by particle or mole. And so if I read this like this, I have 0.015 deuterium atoms over 100 hydrogen atoms. So the reason I don't like to, sometimes I don't like to write it like this is because this is just a small slice of an atom. Can you just take a slice, like say I have a pie and I want just a tiny slice of the pie. Then that's okay to visualize, but can you take an atom and just take a tiny slice of the atom out? Not really. I mean, this is 15 thousandths. So you divide that pie into 1,000 slices and you take 15 of them, and that would be this, 15 thousandths of an atom. So, and then this one would be equivalent to saying I have 0.00015 out of 1. 0.0015 deuterium atoms for every hydrogen atom. So sometimes I don't like the decimal form because it's taking like fractions of atoms. So for every hydrogen atom I find in nature, I'm going to find 0.00015 deuterium atoms. It's fine. I mean, a lot of people can visualize that. But I like to visualize things as like a ball. If I have a big box of balls, then how many of those would be it? And so that's why I try to get rid of it decimal places. So for me, what I do here is I move the decimal 3 over, 1, 2, 3. And then I'll move the decimal over 1, 2, 3 here. So I like to think of it like this. I'm going to have 15 deuterium atoms for every 100,000 hydrogen atoms. So if I have a box that contains 100,000 hydrogen atoms, 15 of those will be deuterium. The rest will be hydrogen 1. But you don't have to do it that way. I mean, all these ratios are the same thing, including in decimal form, it's the same thing. So you just have to recall the units, and they aren't going to tell you the units. When they give you percent natural abundance, they expect you to know that it's not by mass. This goes for a lot of things. Automatically we think of percentages as being percent by mass. We do that for most stuff. So for example, the air in this room is a mixture of oxygen and nitrogen primarily. And everybody knows the oxygen, not everybody, but a lot of people know that the oxygen percentage in this room is what? 22%? 21%?
She had another sick thing on me.
Well, I think of it as like 21%. That's what I normally do. So if it's 21, and in fact, let me look it up. 22, 21. Oops. I already looked it up. Let me see if I still have it up here. So this is from Wikipedia, or not Wikipedia. This is from just Google search here. It's 21% oxygen. We have this little pie chart here. 21% of the pie is oxygen. 78% nitrogen. 1% roughly argon. And carbon dioxide and some other stuff. So here's the pie chart here. So what does that mean? Does that mean if I have 100 grams of air, 21 grams is oxygen?
No.
True or false?
Moles.
That's false.
Change the moles of the future.
Yeah, so what this means is if I have 100 molecules of air, which is a mixture, and so I have 100 molecules of this mixture, how many of those molecules will be oxygen? 21 of those. And so 21 of the molecules or the particles in air will be oxygen.
What indicators should I look for when trying to figure out if something's composition is referring to by mass or by mole? 'Cause
Some of it you have to memorize.
I'm mastering Chem a couple of times. I'm like, what do they mean?
Yeah, so the question is, how do you know if this is by mass or by mole? And the answer for this one is traditionally, it's always by mole, this one, by particles, not by mass.
Good to know.
Also, percent natural abundances are always by mole. Never. And then even if you do this, let me show you this. I'm going to Google search percent comp of air by mass.
Who cares?
So if I do by mass, look what comes up. So I just Googled the percent composition of air by mass, and what did I get?
The percent by mole.
The percent by mole. It gave me the wrong answer. Google gave me the wrong answer.
What's AI?
It's the AI gave me the wrong answer. And so let me scroll down. Is this chart correct? No, that's not correct. This engineering toolbox correct? No, not based on the search engine. I'm sure if you read it, it's not. Let's see. Oh, finally I have. Oh, core is so unreliable. I'm surprised that somebody got it right. There's better sources. Actually, the engineering toolbox usually has it correct. I'm surprised they got it wrong, but it is. It's 23% by mass. Why? Oxygen's a heavier molecule than nitrogen. You know, oxygen weighs 32, nitrogen weighs 28. So
Argon's really heavy.
So it makes sense that the mass percent bumps up for oxygen. And so out of 100 grams of air, 23 grams will be oxygen. And so sometimes it's not written, but there are some percentages you need to know. Percent natural abundance is always by particle. Always. Percent composition is typically by mass. And unfortunately, you just have to memorize that because they aren't always going to tell you what it is. You know, they should say that's percent by mole or volume or even pressure. But I was going to do one other thing here. Okay, so, you know, I shouldn't have stopped here because I don't want to know how many deuteriums I have. In fact, I should have kept going here. Because they aren't asking how many grams of deuterated hydrogen I have. So right now, what I have as far as units go is this. The deuterium atoms cancel deuterium atoms. Molecules of deuterium cancel. U of deuterium cancels. And now I have grams of deuterium, deuterated hydrogen. And so what I'm going to do is this. I'm going to just, actually, I need to first find the percent natural abundance. And what is the percent natural abundance of the molecule? Let's go ahead and do that calculation. And so you, Michael, you do the decimal.
Oh, yeah.
Yeah, that's fine. You could do the decimal. The decimal is going to be the same as this fraction. And so I'll do this fraction. 15 out of 100,000. Times 0.015%. Actually, I'm not even going to put the units in here. You could put the first in fractional or decimal form, and which fraction you use doesn't matter because it's an intensive property. And so this is going to be 15 times 0.015 divided by 100,000. And it might be better just to leave it simple, 0.015 out of 100. Rather than doing it like this. In fact, maybe I'll do that. I like to visualize it like this, and I like to think about it like this, getting rid of the decimal point. But when you do a calculation, you want to minimize your chance of making an error in the calculation. So I'm just going to convert this right into decimal or right into fraction. I like fractions, so I'll just do that. And I get 2.25 times 10 to the minus 6%.
Might I submit that a fraction is in every decimal? Like, when you say it's hard to visualize 0.015 of something, like you said, you like to think of it as like a balloon filled with like beads or something. You can say that was what I thought. It made me think of, well, what if I just imagine that you have like, let's say, however many beads. I don't think that was right. I see your problem. Actually, that would be quite difficult. I don't know. It makes sense in my head.
Yeah, I mean, it could make sense. If you have 100 hydrogen molecules, you'll have 15 1,000ths of a piece of a deuterated hydrogen molecule in there. And so you'll need a whole lot more to put all the pieces together, like Frankenstein or something, to make a whole deuterated hydrogen molecule. That's how you could visualize it. But the same thing here. So this is the percent natural abundance of deuterated hydrogen molecules. And so what I like to do is I like to put this into fractional form to better visualize it for myself. And so sorry for the mess here, but and so putting this into fractional form, this is probably the way I would think about this. And you don't have to do this, but I'm going to write this here. I'm going to get out of scientific notation and write 5 zeros, 1, 2, 3, 4, 5, and then a 2, 2, 5. And then I'm going to get rid of the percentage by dividing it by 100. And then I'm going to move the decimal out of this. So 1, 2, 3, 4, 5, 6, 7, 8. So then I'm going to add 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. And then see what this number on the bottom comes out to. And what is that? 10 billion? 10 billion. And so in fractional form, this is the way I look at the abundance here. The abundance would be 225 out of 10 billion. Is it 100 million? So 8 plus 2 zeros would be total of 10 zeros. So 10 to the 10th. 10 to the 10th would be 10 billion. 10 to the 11th would be 100 billion. So, all right, so 225 what out of 10 billion what? Well, out of 10 billion hydrogens. Oops, not out of 10 billion hydrogen molecules. So the way I like to think of it is if I had a bucket of 10 billion hydrogen molecules, then inside that bucket I should be able to find 225 deuterated, fully deuterated hydrogen molecules, the heaviest ones. Now, can I do this? Is this in grams, or what is this in? Molecules. So when I end up here, this is in grams of deuterated hydrogen. This is not in grams, and grams times grams is grams squared, so this wouldn't work. And so it's not in grams, it's in molecules. So I went too far here. I should back up. And in fact, what I'm going to do is I'm going to back up here. I don't want to go to mass quite yet. And so in this particular problem, I'm going to branch off from the second conversion factor. So we're going to start this problem over again here. And so we're going to go 2.70 times 10 to the 21 deuterium atoms. And then we're going to go to two deuterium atoms are required for one deuterated hydrogen molecule. And so the deuterated hydrogen atoms cancel. And now we have deuterated hydrogen molecules. And then I know that I can get 225 deuterated hydrogen molecules for every 10 billion normal hydrogens or average hydrogens. I should just say average hydrogens. Or, no, I shouldn't even say that, just for every 10 billion hydrogen molecules. Okay, then, do you know what an average hydrogen molecule weighs? 1.008, and then we have two choices for units. It's either 1.008 U per hydrogen atom, average hydrogen atom, or 1.008 grams per mole of hydrogen atoms. And so if you don't like the U to gram conversion and say, you don't want to remember the U to gram conversion, what we can do is we can go from number of atoms to moles by using Avogadro's number. And so that's what we're going to do here. For every 6.022 times 10 to the 23rd molecules, we have 1 mole of molecules. And so the number of molecules cancels, and that leaves us with moles of hydrogen. And from moles of hydrogen, then we can go to grams of hydrogen by using its molar mass. And the molar mass of hydrogen is 2.016 grams of H2 per mole of hydrogen. And so this should give it to us. So let's see what we get here. 2.7 times 10 to the 21st divided by 2 times 10 billion divided by 225 divided by Avogadro's number, 6.022 times 10 to the 23rd times 2.016. And I think I made a mistake somewhere. Did somebody calculate it? The problem with these huge numbers, 10 billion's a pain to put in the calculator. So I'm going to just call it 1 times 10 to the 10 divided by 225 divided by 6.022 times 10 to the 23rd times 2.016. Kind of a big number. You get that? 200,000 grams? Kind of a big number. Maybe I made a mistake. Okay, so the situation comes up in dimensional analysis. Do you remember? Let's say you forgot how to get the percent natural abundance of the molecule, or let's say you forgot how to convert U to gram, or let's say you forgot other things. You shouldn't let that concern you too much. You shouldn't worry too much. And so let's say you get lost and you don't know your way out. What you need to do is you need to try other paths, because oftentimes there's more than one way to get the answer. And so if you get stuck, like, oh, I can't figure out the U to gram, I'm stuck there. Or I can't figure out the percent natural abundance of this molecule, I'm stuck there. There are other ways you can do this. And so what we do is we back up and try a different route. The situation on tests is there's nobody, if you're lost, let's say you're lost in the jungle of this problem, there's nobody coming to the rescue. You're going to have to rescue yourself. And to rescue yourself, then you're just going to backtrack and then try a different path. And it turns out there aren't that many paths we can take. And so let's go back to the beginning here, and we go 2.7 times 10 to the 21 deuterium atoms. And then we figure out all the paths we can go. So for example, one path we can go is we can go to, actually, let me make this a little bit longer. We could go to deuterium molecules. That's one path. And the conversion factor that we use for that is that one deuterium or deuterated hydrogen molecule requires 2 deuterium atoms. Okay, so we might have gone down this path and gotten stuck. So we might backtrack and see, could there have been another route here that we could have gone? And so, yeah, there's another route here we could have gone. We could have gone to moles of deuterium atoms by using Avogadro's number. And that is 1 mole of deuterium atoms contains 6.022 times 10 to the 23rd deuterium atoms. Is there another path we could have gone? Yeah, there is another path we could have gone. And what's the other path? The other path we could have gone is we could have gone from deuterium atoms to hydrogen atoms. How could we go from deuterium atoms to hydrogen atoms? And here we don't have to do this fraction times a percent or fraction times a fraction times a percent. All we do is use their given, and their given was 0.015 deuterium atoms for every 100 H atoms. And so in other words, it's 0.015% deuterium in hydrogen. And so we could have gone to hydrogen atoms. And then do you know where all these lead? All these lead to the same answer. And so if you get stuck on one path, then back up and try. Because you don't have any other choices. Do we have any? Can you think of a fourth choice that we could have done here, a fourth path? And that's the case. In all the dimensional analysis problems I give, there are no more than 3 paths. Most of them, there's only 1 path or 2 paths. So if you get stuck, you back up and you try the alternate path. If there's only 1 path, then you're stuck. You just take it. But all 3 of these can lead to the answer. And so, let's say this one, you're going to require having to do the percent natural abundance of a molecule. And so we did the 0.015% times the fractional abundance. This one, you're still going to have to do that. Some of these you'll have to do U. Others, U to gram conversion. Others, you'll just go moles and skip U entirely, And so there are different routes to this. And so if you get lost on the exam, what I don't want you to do is like find your skeletal remains on the page. And the skeletal remains on the page would be a blank, a blank answer. And so, like this question on the free response, sometimes like five of them will be told. They're easy to grade, it makes my life a lot easier because it's just 0 points, but I'd rather not see that. And the other thing that people do is, well, they're going to go for max partial credit. And they go for max partial credit by stringing together as many conversion factors as they can. But when I look at this conversion factors that they string together, it's like percent times a percent times a percent gives me percent cubed. And I'm thinking, what is a percent cubed? Then it's clear that if you're getting percent cubed, then you don't know where you're going. You're just trying these random things, which is good, but I think you could do better than that. You should be able to do random things like this and at least make sure things cancel out. And so if you're getting weird units like moles squared or grams cubed, then I can't give you any partial credit for that. But if you're getting you're getting stuck and you're getting molecules of this and it makes sense, things cancel out, then I can give you partial credit for that. And so make sure each step makes sense, even if you don't get to the final answer, at least you get partial credit. This is for the test.
What if we have everything set up correctly, and then we do have like an answer, but the answer doesn't match up with work? Like, let's say we just have
Yeah, the setup is correct, but the final answer is wrong. That's why I give extra time. I give extra time to go back and calculate it again. So you should punch it in your calculator again. But let's say you do that and you keep making the same error. That would be a systematic error. You keep getting the same answer. Oh, I must got it right because the second time I calculated, but maybe you hit the wrong key or something like that. Systematic error. And then for those types of errors, I'll give you a 10% deduction usually. And so most of the partial credit you get. I mean, if the setup is clear that it works out. But it depends on the instructor. So some instructors here and at UCLA give 0 partial credit. You either got the right answer or you don't. This is the way they do it. It makes grading very easy because it's just 0 and 1s, and you get a very interesting distribution of grades. A lot of the grades there that we saw aren't a bell curve, a normal curve. A lot of the grades we see there are bimodal distribution. Same thing here. You have the people who got it and the people who didn't get it. And you have 2 camps. Nothing in between. And so it's, even though you might have gotten 95% of the way there, and you get thrown into the didn't get it camp, the bimodal distribution. A lot of people hated those as well. But there are some classes like that. Well, anyway, that's one of the, if not the most common ways of solving problems, and this goes for the advanced problems. The advanced problems, a lot of those advanced problems are just like, your basic problem, but 1 extra step or 2 extra steps. Or like the alcohol one. The alcohol one that we did can be thought of as 2 unknown, 2 equation. In other words, system of equations. But I separated it into 2 problems for that particular one. All right, we're going to go back to chapter 3 now. And did I talk about combustion analysis already? Briefly? All right. Combustion analysis is a great way for analyzing organics. Most of the organics burn quite easily. And organic compounds will contain carbon and hydrogen. And other elements could be present: oxygen, sulfur, nitrogen, phosphorus, etc. And so when we burn carbon and hydrogen and oxygen containing compounds, we get CO2 and water. If there's sulfur present, what do we get? You know what you get when you burn sulfur? You convert it into what? If you burn carbon, you convert it into CO2. And CO2 is the max there. And we call it complete combustion. So complete combustion of carbon and carbon-containing compounds yields CO2. We've used it to the max. So if your body is great, because if you want to completely consume the alcohol, if you drink alcohol, then you're going to burn it all the way to CO2. And burning is not literal in the body. Your body's going to oxidize it to CO2. And you can't go any further. We've extracted all the energy that we're going to get from the carbon-containing compounds here. CO2 is the max. But when you burn sulfur, what should you get? Okay, when we burn it to the max, that is, if we want complete combustion of sulfur, what should we burn it to? SO2 or SO? Maybe SO4?
What do we get when we burn sulfur all the way?
Yeah, what do we get when we burn sulfur? When we burn carbon all the way, we get CO2. If we burn sulfur all the way, we should get...
Out of the room as soon as possible?
Yeah, you should get out of the room as soon as possible. Even with CO2, high concentrations of CO2 are bad as well. But if we burn sulfur, we should get, if we do complete, we should get SO2. Sulfur and carbon, are they in the same family? No. Do you know what we should get if we burn it completely? SO42 minus, but in the gas phase, we don't have SO42 minus. We're going to have the equivalent to it, and it's going to be SO3. Why SO3? Because what is the max oxidation state of carbon in CO2? +4. What is the max oxidation state of sulfur? +6. And so we should burn it all the way to sulfur 6. Carbon goes all the way to carbon 4. And so if we had the Roman numerals there, it would be Roman numeral 6 or group 6. However, when we burn sulfur, it usually doesn't form SO3 initially. You know what it forms? SO2. So it's not complete, but this is what we get. It takes a little bit more to convert SO2 to SO3. And so we form SO2 initially, eventually it goes to SO3 with time. And so this is in the future, but SO2 is what we get. When we try to do complete combustion of sulfur-containing organics. What about nitrogen? Nitrogen doesn't burn so cleanly. Sulfur burns pretty cleanly. We form SO2. Cleanly means we don't get a whole mix of product. Nitrogen, we get a whole mix. So when we try to burn nitrogen, we get things like N2O, nitrous oxide, NO, nitric oxide, NO2, nitrogen dioxide, N2O4, dinitrogen tetroxide. We get a whole mix of product. And so it makes a mess. And since it's a whole mix of products, we call it NOx. And so when we burn nitrogen-containing compounds, we get NOx, where X is a variable. And so X can be one oxygen. It could be two oxygens. It could be half an oxygen. If it's half an oxygen, then it's N2O, or nitrous oxide, or whatever. And so nitrogen, we get more of a mix of products. And whereas sulfur, it kind of just goes to SO2. And so those complicate things. Phosphorus, what do you think we'll end up with? Carbon, we form oxides of carbon. Hopefully we don't get carbon monoxide. We get carbon dioxide. Sulfur, we get oxides of sulfur. nitrogen, we get oxides of nitrogen. And so NOx are called oxides of nitrogen. And so, did you know it's possible to burn a little bit of air? Air is mostly what? Air is mostly nitrogen, but it only happens at extremely high temperatures and pressures. Then you can burn the nitrogen in air. And so what happens is, this happens in diesel. In diesel engines, they have extreme pressures and temperatures. So in diesel engines, the nitrogen in air burns in oxygen, and you form NOx. Not as bad in gasoline vehicles, but NOx can also form in gasoline vehicles because in the ICE, the internal combustion engines, there's a piston and you get high pressures and high temperatures in there. And during the combustion process, a little bit of the nitrogen can burn. And that little bit of nitrogen that burns forms NOx. And then for every 2 years, if you have a gasoline burning vehicle, you have to bring it to the smog station, and they check for NOx. But the NOx shouldn't be very high. The NOx should be quite low because all those vehicles have a catalytic converter. And the catalytic converter, do you know what a catalytic converter does? Is it takes this whole mixture of NOx and converts it into, do you know what it converts it into? Not carbon, it converts NOx into nitrogen gas. And so it comes full circle. So a little bit of nitrogen burns in the engine, goes through the exhaust, hits the catalytic converter, and the catalytic converter reconverts it back into nitrogen. And nitrogen's safe, it's not a greenhouse gas, So we're good. And so that's pretty good. And so let's take a look at some combustion analysis problems from the book. This would be in chapter 3. Did I already have it open? Thought I did. And this is the other thing I like to do when I study for tests, is I like to look at all the homework problems. I don't like to do all of them. I just like to look at them and then understand how I'd solve it. And sometimes you don't understand, you just look at the solutions guide. But here I have a 0.1880 gram sample of hydrocarbon. Hydrocarbon means there's only hydrogen and carbon present. This would be things like methane, ethane, propane. There's no oxygen, no nitrogen, no nothing other than carbon and hydrogen. So all the carbon ends up in CO2. So in this combustion analysis, I'll take my grams of CO2. From grams of CO2, I'll go to moles of CO2. From moles of CO2, I'll go to moles of carbon and stop. And then I get 0.1602 grams of water. And so I'll go from grams of water to moles of water to moles of hydrogen, and stop, moles of hydrogen atoms. And so once I get the moles of carbon atoms and the moles of hydrogen atoms, I get the simplest whole number mole ratio. And that would be its empirical formula. And so you get that. If I want the percent composition, I could go one extra step. And so I go from moles of carbon to grams of carbon. And then I have the total grams. So grams of carbon over the total mass times 100% gives us 100% carbon. And the same thing, I go one extra step here. I go from moles of hydrogen to grams of hydrogen and then figure out the percent composition there by mass. So this is nice. They said mass percent composition, so we know it's by mass. Okay, then for the molecular formula, I would need to know its molecular mass. This is molecular mass. So do you guys remember how to go from an empirical formula to a molecular formula? You know, you determine the empirical mass and compare it to the molecular mass. If they match, then they're the same. If they don't, it's a multiple. So the molecular formula is some multiple of the empirical formula. You just do it that way. So this is like a Chem 4 style problem. The only trick is that we aren't directly given grams of carbon. We have to figure out that from stoichiometry. Okay, paracresol is used as a disinfectant in the manufacture of herbicides and in the manufacture of herbicides, excuse me. A 0.4039 gram sample. So they tell us the total sample of carbon, hydrogen, and oxygen. And so here we have to know that there's oxygen in there because the oxygen gets mixed up in combustion analysis. In combustion analysis, we lose track of oxygen. And so we have to get oxygen in a different way. Did I already talk about this? No? Okay. So let me talk about it right now. So in combustion analysis here, the carbons end up in CO2. The hydrogens in the original unknown end up in water. But the oxygen, we don't know the oxygen because we have oxygen from air and oxygen from our sample. And so we lose track of that. And so we don't know, how much of this comes from air and how much comes from our sample. And we always use excess oxygen so that we get complete combustion. So we completely lose track of the oxygen. And so what we have to do is we have to determine the amount of oxygen by the mass difference. And I'll talk about the mass difference. The mass difference is this. This molecule consists of carbon, hydrogen, and oxygen. So if I take the mass of this molecule, subtract out the mass of the carbon, subtract out the mass of the hydrogen, then all that remains is the mass of oxygen. And so I can figure out the amount of oxygen in grams based on the mass difference. Once I get the mass of oxygen in grams, then I can convert it to moles. And then I'll take the mole ratios of the three, carbon, hydrogen, and oxygen. And so this is how we determine how much water and how much CO2 is formed here by combusting the sample and then capturing the water, like in a desiccant, like a dry array, and then capturing the CO2 in something that absorbs CO2, and then weighing these. So we weigh these before and after, and then we can determine how much of each of these we have. So when we do this, we have the grams of CO2, so we go from grams of CO2 to moles of CO2, moles of CO2 to moles of carbon. And normally we stop at moles of carbon because an empirical formula is the simplest mole ratio. But here we have to go one extra step automatically. We have to do one extra step because we have oxygen. And the only way we can get oxygen is by the difference in mass. So we're going to go from moles of carbon to grams of carbon. And so out of this 0.4039 gram sample, we know how many grams of carbon we have. That's from this calculation. Then over here for the water, we'll go from grams of water to moles of water to moles of hydrogen. And again, we normally stop at moles of hydrogen to get the simplest mole ratio here. But we're going to go from moles of hydrogen to grams of hydrogen. And so we know how many grams of hydrogen in here. And so the difference will be the grams of oxygen. So we'll take the total mass minus the grams of carbon from the CO2 minus the grams of hydrogen from water, and the balance will be oxygen. And then we'll go from grams of oxygen to moles of oxygen. So we'll go back to moles and get the moles of all of these and get the simplest mole ratio of carbon, hydrogen, oxygen here. And that will be the empirical formula, the simplest whole number ratio. And then we'll compare the empirical mass, how much this weighs, to the molecular mass. The molecular mass of this is 108 and C. It's going to be a multiple. The molecular mass is a multiple of the empirical mass, like an integer multiple. So it'd be 1 times if it's the same, 2 times if it's twice as heavy, 3 times, etc. All right. Dimethylhydrazine is a carbon, hydrogen, nitrogen. Now, we could do nitrogen in the exact same way we did oxygen. We could just do it by difference, but they're throwing one more wrench into your brain, the mechanics or the workings of your brain. And so let's take a look at what they're doing here, because what we can do is we can just take this total sample, 0.312, minus the grams of carbon, minus the grams of hydrogen, and all that's left will be grams of nitrogen. So we could solve this problem just like we solved the previous one. However, they want us to solve it a different way. And in this particular problem, is this. Now, I need to take a step back. How do they know there's no oxygen in here? How did they know there was no nitrogen in the previous one? Well, they had to do pre-experiments before doing this. They had to do an experiment to determine that there was oxygen in the previous paracresol. And it's actually not that difficult to do. You can do it based on the vibrations, which we call vibrational spectroscopy or infrared spectroscopy. There are other ways of doing it. And so here they had to know that there's nitrogen, no oxygen, no phosphorus, no nothing else, just nitrogen. So there's some other experiment that led us to this. And this information we need to know. While we need to know what it is in order to get the correct empirical formula, but if it's just a hydrocarbon, then everything should add up to 100% with carbon and hydrogen. But anyway, from this we got CO2 that gives us carbon. We have water that gives us hydrogen. Now how do we get the nitrogen? In this particular example, the nitrogen content of a 0.486 gram sample. So what they did was they took an entirely new sample. The original sample was 0.312 grams, so they have a second sample. The second sample was analyzed for nitrogen. So what they did was they burned the nitrogen. When you burn these nitrogen-containing organics, what do you form? NOx. And then they passed it through some catalyst, and when they passed it through some catalyst, they converted it back to nitrogen. And then they captured the nitrogen, and they captured 0.226 grams of nitrogen. So what we can do from this, and this is a bit tricky because we can figure out how many moles of nitrogen are in here, but this was not analyzed for carbon, and it was not analyzed for hydrogen. And so what we have to do in this particular case is get the percent by mass nitrogen. The percent by mass nitrogen in these two samples should be the same. So once we know the percent by mass nitrogen, we can come up here and then figure it out, how much nitrogen's in there. Does that make sense? But that's kind of the long way of doing it, because if we did it the oxygen way, it would be a lot faster. Okay, let's look at 46. The organic solvent, thiophene, is carbon, hydrogen, sulfur. So now we have sulfur. This is different. But we know that when sulfur-containing organics burn, what does it form? SO2. So this is easy. We get the carbon from here, the hydrogen from here, and the sulfur from here. So all the sulfur ended up in SO2. So sulfur burns a lot cleaner. That is, we don't get a lot of different products. And so this is reliable here. Just analyze for the SO2. If it didn't, let's say we get some SO3 in there, we get some SO in there, then it complicates things, you know, as far as the analysis goes. Okay, and then the rest of the problems are very similar. You know, here's another sulfur going to SO2. And that was the entire variation of problems. And so I'd look at all the variations of the problems and see if I could figure them out. Okay. All right, since I'm behind, I want to just make sure I get through chapter 3 here. For the organics, actually, let me... We talked about hydrates a little bit. This is cobalt-2 chloride hexahydrate. Cobalt-2 chloride hexahydrate is pink, but if you heat this up, it drives off the waters of hydration, and we have anhydrous cobalt-2 chloride. Anhydrous cobalt-2 chloride is blue, and cobalt-2 chloride is sold. And do you know what it's sold commercially, and do you know what the name of this stuff is? The name of this stuff is called dryerite, and dryerite people use in desiccators. Do you remember your desiccator? Your desiccator had hopefully blue anhydrous cobalt 2 chloride. The blue anhydrous cobalt 2 chloride sucks water out of the air. When all of your blue turns to pink, then it's no good anymore. We don't have to throw it away, fortunately, because you know what we do? When that desiccator turns pink, we throw it in the oven, heat it up to about 120 degrees, and pretty soon it goes back to blue. You just drive off all the water and dry it up. Okay, as far as organics go, I'm just going to keep it simple here. And so you should know like methane, ethane, propane. Things like benzene, no. You don't need to know benzene. You don't need to know ethene. We'll just keep it simple. You should know these. Oops. Meth, eth, prop, those. Isomers I haven't talked about yet. Over here, for alcohols, you should know these two. Ethanol and methanol. Those are two important ones. Propanol and isopropyl alcohol we'll deal with later. But know those two, methanol and ethanol. For carboxylic acids, you should know these two here. Formic acid and acetic acid. You know, methanoic and ethanoic acid. And that should be good for the organics. What I want to do, so I don't get too far behind, is I want to talk about Chapter 4 a little bit here. In Chapter 4, I'm going to just kind of summarize it to keep it short. Like if you look at the UCLA Chem book, the UCLA Chem book crams our first 4 chapters into 1 chapter, you know, because they just call it review. And so a lot of these topics are, but they also use a majors book. So it's the book is designed for chem majors, but they make everybody use it. But stoichiometry, what do we need? We need a balanced equation. So the first part of Chapter 4 deals with balancing chemical equations, but you've done that before, right? Balancing chemical equations.
A review would help. I don't know about everyone else, but
A review would help? Okay.
that was really helpful.
Yeah, balancing equations. We'll look at a review of some of the parts for sure. And then we had, you know, your standard stoichiometry problems. Do you remember like grams of A to moles of A, moles of A to moles of B, moles of B to grams of B? Okay, good. And then we had theoretical yield, percent yield, actual yield. Do you remember all those terms? All right, so the difference between, let's say, Chem 4 and Chem 1A is we're going to have a lot more percentages. So not only do we have these types of percents here, but we're going to have like percent composition. So, for example, we might be working with air instead of oxygen. And so I might say grams of air. If I say grams of air, then you need what? You need the mass percentage of air. Or if I say like moles of air or molecules of air, then you'd need the mole percent of air. And so air is a common one, so it depends on what I give you on the problem. And so we have like little extra things that we do. So like a typical Chapter 4 type problem would be, let's say, like this, where it gets a little bit more complex maybe. Chalkboard chalk is made from calcium carbonate, calcium sulfate with minor impurities such as silicon dioxide. Silicon is a semi-metal, so we didn't name this either as a molecular compound, silicon dioxide, or a ionic compound, silicon 4 oxide. It's quartz. Only the calcium carbonate really reacts with dilute HCl. What is the mass percent calcium carbonate in a piece of chalk? It's a 3.28 gram sample yields 0.981 grams of CO2. And so here we have different percentages, but you know the stoichiometry is the same. We just look at what's given. And so we have 3.28 grams sample, but we don't know what its composition is. We have 0.981 grams of CO2. So in this particular stoichiometry, I'd start with 0.981 grams of CO2. But what do we do with this sample, and how do we get the percent? What is the mass percent calcium carbonate? Well, the mass percent calcium carbonate is the grams of calcium carbonate over the total grams. So the total grams would be 3.28 grams of sample times 100%. And so this is an advanced problem, 96, and we're just trying to solve for the grams of calcium carbonate. But this is pretty simple, because it would be grams of A, CO2, to moles of A, moles of CO2, moles of CO2 to moles of B, which would be moles of calcium carbonate, and then moles of calcium carbonate to grams of calcium carbonate, and then we're done. And so that was an advanced problem. And so the advanced problems is like one extra step or something. And this would have been a Chem 4 level advanced problem too. All right, I'm out of time here, so let's stop. Thanks. But we're not going to have, again, we're not going to have all of Chapter 4 on this, just basic stoichiometry. Wednesday. Exam's on Wednesday.